Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part 3 of the lecture on coincident frequency analysis. This is the 12th lecture in the course on statistical methods in hydrology. Part 3 is about using Monte Carlo simulation to evaluate our coincident frequency problem, meaning to do an analysis that is based on multiple variables. Now, we watched the Monte Carlo simulation video yesterday, I think, and I described Monte Carlo simulation as replacing the probability distributions of random variables with large random samples from those distributions, right? So what we're doing is replacing the probability distribution of our variable A and our variable B with large random samples. So we're creating events with a value of A and a value of B. Now, if A and B are correlated, we're going to use correlated random sampling to maintain the observed correlation between A and B. If they're not correlated, we would just sample A and B independently, right? Then we're going to evaluate our variable C for each event, which is a value of both A and B. So we'll do some kind of modeling, right, to get the response of variable C given A and B. And we'll end with an output sample of C from which we can infer the probability distribution of C. So I'm going to switch over from our tributary flow example to evaluating the annual peak pool stage frequency curve for a flood reservoir. So one of my inputs is the inflow to the reservoir as a flow frequency curve, and the other input was the starting reservoir storage. Okay, so to do the Monte Carlo simulation, I'm going to replace this flow frequency curve with a large sample of values from this distribution. So I'm going to generate random uniform 0 to 1 values, and I'm going to put them on the exceedance probability axis, bring them up to the curve and over. For each of those flows, I'll turn it into a hydrograph and then bring it over to a reservoir analysis. Right? Now, I'm also going to generate a random uniform 0 to 1 value to sample the starting pool level in the reservoir before the flood event. Right? Then with that hydrograph and that starting pool, I'm going to do the reservoir routing and compute the peak pool level from that event. So that peak pool stage is the result of one event or is one sample member in my ultimate distribution of variable C. Right? After doing this many, many times with many flows and many starting pools, I'm going to end up with a large sample of peak pool stages. Right? So to look at that in a different way, I'm going to generate, say, 1,000 events. Here is 1,000 annual peak flows from my flow frequency curve. On the left, I'm showing them in the PDF form as a histogram plotted on top of the original probability distribution. And on the right, I'm showing them in the CDF or frequency curve form, where each of my 1,000 flows is plotted against plotting positions on top of the frequency curve form of my distribution. Note the plotting positions are based on n equals 1,000 because this is a sample of 1,000 flows. Now for each of those flows, I also sampled an initial reservoir starting pool, and then from each I can compute the peak reservoir stage for my reservoir simulation. So here is my sample of 1,000 peak pool stages that results. Right, here they are in the histogram form, and on the right we have them sorted and plotted against plotting positions in the frequency curve form. Right, so this output is what I'm looking for, which is the frequency curve for the annual peak pool stage, resulting from my Monte Carlo simulation. So when do I need to sample correlated values? Well, this is when I suspect there's enough correlation between my variables A and B to make independence a poor assumption. Right, so first I have to evaluate coincidence. Right? Did they experience the annual maximum at the same time? Am I seeing the annual maximum of my variable A at the same time as the annual maximum of my variable B, or is variable B just any given day when I'm having my annual max on A? Then I'm going to study and estimate the correlation, right? For flow, I'm going to consider the correlation of log as well as linear flow, right? And then I'm going to estimate probability distributions for each of my variables. So here I've moved back to my tributary flow problem, right? So I've got variable A, which is flow on my tributary, and I've got variable B, which is flow on my main stem. Here I'm seeing the annual maximums at A and a fitted frequency curve, and I'm seeing some events at B with a frequency curve fitted to those. Now, if I plot correlation, I'm plotting each value of A against each value of B. And on the left, I'm showing it with linear axes, And on the right, I'm showing the same values with log axes, right? And you can see with linear, the correlation is 0.74. And in this case, when I transform to a base 10 log flow, my correlation is 0.84. Right, so now when I do my correlated sampling, I want to be able to reproduce both these correlation plots and my frequency curves. So if I generate 1,000 correlated values of each, maintaining the correlation and the distributions, on my left I have the linear, on my right I have the log space. And I'm going to go back and forth from the original data to the simulated random values, right? The original data and the simulated random values, you can see that the shapes are maintained, right? And also the marginal distributions of both A and B are maintained by these 1,000 random flows. Now, if you're looking at the PowerPoint slides, there's also a slide for the method for generating the correlated random values. So if you want to take a little bit more time, look at the PowerPoint and see that method. I'm not going to take the time in this video. Right, so we're back to the tributary stage problem. And we're working now with a frequency curve for tributary flow and a frequency curve for the mainstem flow. And these are the two probability distributions that I'm going to replace with random samples, right? So I'm going to now generate correlated random values that are uniformly distributed between 0 and 1. For each pair, I'm going to come and get the flows off my flow frequency curves, turn them into hydrographs. Then I'm going to drop those hydrographs into my hydraulic model, the A on the tributary, and the hydrograph for B is the mainstem. And then my hydraulic analysis is going to compute the stage at damage area C, right? And that will be the result of one event. And if I generate all my 1,000 pairs of A and B and simulate each of them, I'm going to end up with a sample of tributary stages C, right? This is the histogram form. And then if I rank and plot all of those values against plotting positions, I'll have a stage frequency curve for C, which is the output I was looking for. So like we saw in the third part of the Monte Carlo lecture, we noted that we don't yet show knowledge uncertainty in this analysis, right? We've just looked at computing a best estimate of stage frequency curve at C based on the natural variability in flood magnitude on my tributary and on the mainstem. Right? But I have uncertainty in those probability distributions, and I also have some uncertainty in the parameters in the hydraulic model. And the natural variability and the knowledge uncertainty both have different effects on my result. Right? So all the natural variabilities will be captured in the frequency curve of stage at C. The knowledge uncertainties are going to make us uncertain about where that frequency curve lies. We capture this in the same as we saw in the third video of the Monte Carlo simulation for flood damage. We're going to do a two-level nested Monte Carlo. Okay, we're going to sample instances of our natural variabilities as flood events, right? Meaning natural variabilities are defined as things that vary event to event. And we're going to do enough flood events to capture the distributions of flow. Right? This is the inner loop of our Monte Carlo simulation. And the inner loop is going to allow us to compute a stage frequency curve. Right? We're also going to sample instances of our knowledge uncertainties in the model parameters and in the parameters of the probability distributions for each realization of a stage distribution. Right? So the knowledge uncertainties are sampled in an outer loop, right? That allows us to compute the uncertainty in the stage frequency curve. So each time around the outer loop is called a realization. Right? So to look at these one piece at a time, all of our inner loops are going to span natural variability. And this is called one realization, and it's going to give us a sample of peak stages at C. Right? Now with those peak stages at C, I'm going to rank and plot them versus plotting positions to get an annual peak stage frequency curve at C. Now this results from one outer loop B, also called one realization. Right? Now, note my color coding. I've been showing the natural variabilities in green and knowledge uncertainties in orange, right? So one realization spans all my natural variabilities in green. So one peak frequency curve at C results from one realization, right? Now I do additional realizations, meaning additional outer loops, to start exploring the uncertainty in my model parameters. Right? And after I've done many realizations, I'm going to have many peak stage frequency curves at C to plot together, right? So when I've done many of these, I've spanned my knowledge uncertainty. I show that knowledge uncertainty by this um, PDF of uncertainty shown at the 1% stage. Note that PDF of uncertainty should be visualized as coming out of the screen, right? And this shows my uncertainty in what the 1% stage is. And then I can also plot a 90% or a 95% confidence interval, also shown in orange to show that it is reflecting our knowledge uncertainty. Right, so let's compare the total probability theorem method to the Monte Carlo simulation method, because we could have evaluated that same problem with the total probability theorem. Right? How does the Monte Carlo, which I didn't mention, but this is analysis that we can do in HEC Watt with the FRA computation. So the watershed analysis tool with the flood risk analysis computation option, right? How does that Monte Carlo analysis differ from the total probability theorem method? Well, first we can explicitly incorporate the uncertainty in flow frequency curves and other variables like starting pool stage. We can easily capture more random variables than just peak flow and channel stage if they're relevant, meaning more than just two. We can capture any number of variables we want to in the Monte Carlo simulation. And if you recall, the total probability method was based on two variables. So if we're modeling flood events, we can consider a range of different event shapes with differing volumes for a given peak magnitude. So we can have a lot more variability in things like the shape of the event going into the Monte Carlo simulation, because we're simulating a lot more events than just what our matrix in the total probability method for the response surface would have provided. And finally, correlation. It's a lot easier to capture correlation in the Monte Carlo simulation method because we can just do correlated sampling with our marginal distributions of variable A and variable B. We don't actually have to develop a joint distribution of A and B. Right, so here's one more example of working with more variables. And in this case, this is the same kind of picture, but with more elements. We're going to start now with a precipitation frequency curve instead of a flow frequency curve. So we're going to replace the precipitation frequency curve with a big sample of annual maximum precipitation depths of some duration. And for each of them, we're going to generate a hyetograph. We're going to bring that into a rainfall runoff analysis, right? Maybe we're going to randomly sample infiltration rate as an actual variability. From that model simulation, we're going to generate hydrographs. We're going to bring those hydrographs into our reservoir analysis where we sample a random starting pool, and then from routing that hydrograph, we'll get a peak pool and thus a peak stage, and end with a sample of pool stages and therefore a pool stage frequency curve, right? So in the Monte Carlo simulation approach, we can have any number of random values and we can have any number of watershed models being used within our analysis. So that is the end of part 3 of the coincident frequency analysis lecture. If you have questions, please share them.